Hey guys, today we're going to be talking about Type 1a supernova. These explosions are totally bright, ridiculously destructive, and surprisingly consistent. But what exactly causes them? And what's happening inside that makes them so explosive? And why are they so interesting? Let's break it down. No dancing.
Please.
First things first, what is a white dwarf? These are seriously dense. We're talking a mass similar to the sun crammed into something the size of the Earth. It's like squeezing a watermelon's worth of mass into a grain of sand. Imagine a sun-like star that has run out of its fuel. When it can no longer keep nuclear fusion going in its core, it sheds its outer layers in a dramatic cosmic shrug, leaving behind a super dense core called a white dwarf. Hence, this is why I say that white dwarfs are the size of the Earth but the mass of the sun. These white dwarfs are basically stellar corpses, quietly cooling off until they get a little too greedy. Here's where things get a little spicy. Many white dwarfs are in binary systems, meaning they have what we like to call a companion or a donor star hanging out nearby. These white dwarfs and their companion donor stars essentially rotate around each other, around a central point. And this is why they're called binary systems. But instead of being a good white dwarf neighbor, the white dwarf starts stealing mass and stealing material from its partner.
Oh, he's stealing!
This mass, which is being accreted by the white dwarf, is mostly comprised of hydrogen and helium. The white dwarf accretes this mass from its companion star until the white dwarf reaches a critical limit. This critical limit is 1.44 solar masses, which we call the Chandrasekhar limit, named after famed Indian-American physicist Subrahmanyan Chandrasekhar. The hydrogen and helium on the white dwarf's surface now is essentially a layer of fresh fuel. It's a cosmic all-you-can-eat buffet, but with the Chandrasekhar limit. But what happens after the white dwarf reaches the mass limit? Let's find out. At the point where the white dwarf has reached the Chandrasekhar mass limit, it essentially tips the scale and starts a runaway reaction. How does this happen? Well, we know that a white dwarf is a very, very small remnant of a star. But once that white dwarf has gained enough mass to surpass the Chandrasekhar limit, that white dwarf's density and pressure and temperature start skyrocketing. It becomes so intense that the carbon and oxygen nuclei in its core start to fuse. This is where the real chemistry magic happens. Carbon nuclei smash together to form elements like neon and magnesium, releasing an incredible amount of energy. And once fusion starts, it's a runaway reaction. More carbon ignition means more energy, means higher pressure, higher temperature, and it's just a positive feedback cycle. The fusion spreads throughout the white dwarf in a matter of seconds, faster than you can say thermonuclear detonation. The energy released is so immense that it overcomes the star's gravity, blowing the entire thing apart. Now to the real question. Why are these explosions so bright? The reason these explosions are so bright comes down to the amount of energy released. Carbon fusion produces heavy elements such as nickel-56, and these decay into cobalt and eventually iron-56. This is because nickel-56, cobalt-56, etc. are unstable elements. And when they decay into the next element of that process, they also release gamma rays and other radiation as a part of that decay process, adding to the brightness. For a while, the supernova can outshine the entire galaxy it's in. Now, why are Type 1a supernova so predictable? Let's start from the beginning. A white dwarf starts with mass accretion from its donor or companion star. Once it reaches the Chandrasekhar limit, which is a very important limit, it then explodes. That limit is the reason that they're so consistent. Since all Type 1a supernovae happen when a white dwarf reaches that Chandrasekhar limit of 1.4 solar masses, that means that they explode with roughly the same amount of intrinsic brightness. The peak brightness and how fast it fades tells us a ton about the explosion. This is due to the fact that every Type 1a supernova should have the same absolute magnitude of brightness. It's like having a universal measuring stick for the cosmos, but instead of inches or centimeters, we're talking light years. We'll talk more about this cosmic measuring stick in the next video, so stay tuned for that. Make sure you hit the subscribe button so you can learn about how these super bright events in our universe can help us learn about dark energy and dark matter. Anyway, now we wonder what happens after the explosion. After the explosion, all that remains is a cloud of debris and gas expanding into space. This debris is called the ejecta of the Type 1a supernova. Now, this gas and debris cloud is rich in heavy elements, such as iron and nickel and silicon and others. These elements are eventually recycled into new stars, new planets, and sometimes maybe even life. So the next time you're feeling a little low, just don't forget that the iron in your red blood cells could have come from a Type 1a supernova. Talk about a blow up, right? So that's how a Type 1a supernova happens. It starts with a greedy white dwarf, builds up to a runaway fusion reaction, and ends in
5 big booms. Boom!
one of the brightest explosions in the universe. It's a cosmic fireworks show,
Boom!
but with some serious science behind it. What do you think? Is this one of the coolest cosmic events you've ever heard of? Or are there any other cosmic phenomena that you'd want to learn about? Let me know in the comments. Thanks for watching my video, and keep looking up, guys. See you next time. Don't forget to like and subscribe. It's free, and you can change your mind at any point in time, and it really helps me out as well.